speaker will talk YI, and it is Professor Jayme Vaz, which is an associated professor at UNICAMP, the Department of Mathematics. He works with mathematical physics, so algebraic structures, right? He had visiting positions at Syracuse University in the USA and also in Waterloo in Canada. So it's a great privilege to have you here. Please, all yours.
Thank you very much. Good morning, everybody. First of all, I would like to thank the organization of the Congress for the very kind invitation, the possibility to talk to this young audience. I really love to talk. It's the kind of audience I love the most to talk, so I hope you enjoy also the talk. I apologize for my terrible English accent. Even my Portuguese accent is terrible. I have a caipira accent, okay? So it's terrible. So my Portuguese is terrible, so can you imagine the English one? So I'm sorry for that. I received the instructions to give a talk, which is to be a general talk, a non-technical one, and I swear that I try to do my best to be a non-technical talk, but it's a rather technical subject, so I'm afraid I was not 100% successful with that, but I tried to do my best. The subject of my talk is something that is occupying my mind, say, for at least 30 years or so. I started, I think, at the age of most of you, when I was in my third or fourth year of my undergrad course. I made my bachelor in physics at the University of São Paulo. And at that time, I was very much interested in the foundations of quantum mechanics. Okay? And then when I started studying quantum mechanics, I will show what I have in mind in a few seconds. I started studying complex numbers, and well, I asked myself, why do you have complex numbers in physics? I'm not talking, when I say about complex numbers, I'm not thinking about the situation when you have, for example, you are solving a differential equation, second order differential equation, constant coefficients, then use a complex exponential, okay? It is easier to do it using complex exponential, but you don't need to use it. You can work with sine and cosine functions, no problem with that. Sometimes after this, you want to study, say, some classical polynomials, solutions of Schrödinger equation for hydrogen atom, for harmonic oscillator. So you have Lagrange polynomial, Hermite polynomials, and then you start studying hypergeometric functions. Okay? And you see that they are Fuchsian equations, and you see that it's easier to study than using in the complex plane. And more than that, if you you compactify it with the point at infinity, you work in the Riemann sphere. So things are much easier, okay, when you are working this Riemann sphere than in the real line. But you don't need it. Things are easier to do it. That's why in most situations, there are a lot of situations when you have this quotation from Paul Panavé, which I agree almost 100% with it. In a free translation, saying that sometimes it seems that between two truths in the real domain, the easiest and shortest path goes through the complex domain. Okay? But this is, as I said, a tool. It's not this kind of situation. Okay? I'm looking for a situation more deep than that, which is, I think, is in the realm of the physics, of the geometry involved in the problem. And as I said, I was studying, at that time I read a lot of papers from Niels Bohr about the debate between Einstein and Bohr. And one day I read that paper. This, oops, it's here. Here. One day I had in my hands this paper from Bohr on the notions of causality and complementarity, published in 1948 in this journal, Dialectica. And well, in the first pages of the article, we have this part of the test where you can find equation 1 and 2, the well-known expressions for the momentum operator and the commutation relation between them. And there you have the square root of -1. Okay? And then a little bit below this part, the next paragraph, you find this part of the test. And then you have, which is highlighted in yellow. These symbols themselves, as indicated already by the use of imaginary numbers, are not susceptible to pictorial interpretation. I don't remember exactly what I was thinking at that time, but probably it was something like, what the hell? Something like that. What does it mean? Because there is imaginary numbers, is not susceptible to any kind of interpretation. So at this time I said, what is really complex numbers? Why they are there? Why they are complex numbers in physics? So I started being interested in that, and after that, I say, this is 30 years ago, I read a lot of that, a lot of things involved with complex numbers. So I'm trying to understand these kind of things. The interpretation, why these relations in quantum mechanics you need complex numbers. Well, I think when you have an enemy, the best way to beat it is to know his history. Okay? So I would like to start with some history about complex numbers. I don't know if everybody here is aware of it, so I start with the history. The history of complex numbers started in the north of Italy in the beginning of the 16th century with duels in public squares. Well, you might think that you have a Wild West style in the north of Italy, where one man on one side with a gun, another man on the other side with another gun, they fighting for a girl, but it was not like that. It was mathematical duels. What happened at that time? One guy defied another one. Well, money is involved, of course, and defy another one with some. There's a bet. People bet who will win, who will lose. And well, what they played? They proposed algebraic problems, mathematical problems, but algebraic problems to each other. Okay. When you propose the problem, you are supposed, of course, you know how to solve that problem. So you send the problems and their answer to a public notary who keep them safe. The other guy do the same. And at the great day, at the deadline, they see, well, the answers, who gave the answers to the problem, those who solve more problems, the winner. Okay? And at that time, there is a great winner at that time. It was Scipione del Ferro. Here, Scipione del Ferro. He was a very good one on these duels, mathematical duels. And when he was dying, he had a student, Antonio Fiori, who was not a brilliant mathematician, okay? But by some reason, when at his deathbed, he gave his secret formula. That's why Scipione del Ferro was so good. He had a secret formula to solve some kind of equations, cubic equations. Okay? And he gave to Fiori this formula, which is this one. Okay? At that time, this is the cubic equation. It's very interesting to note that, see how the cubic equation is written. It's written in such a way that the quantities are always positive. Okay? They are always positive. The problem was not to take a square root of a negative number. Well, of course, this is a problem, but the problem is negative numbers. At that time, people don't believe in negative numbers. It's not like us today that understand, well, negative number, if you have a negative number in your bank account, you have a problem. Okay, you understand the meaning of it. Okay, at that time, they don't understand, know how to deal with negative numbers. So how to think about square root of negative numbers. Okay? So they are all written in a way that they are positive. You have, of course, the subtraction, but you always subtract the bigger from the minor. Well, one from another, but the bigger, and then the other. As in this equation. Okay? As you see, see, all the numbers here are in such a way that the quantities are positive. But so nobody knew this formula. So you change P and Q for different numbers, so you have many different problems, and then, okay, you win a lot of duels. So Fiore said, now I am the guy, okay? So he went to Venice to defy another guy there who was good at these problems. The guy is Nicola Fontana, also known as Tartaglia. Tartaglia in Portuguese is gago, in English stutterer. You see the word in English is very good for that. To say stutterer is very difficult to say the word. It's very appropriated. So he went there. He went there to Venice, proposed some problems to Tartaglia, but Tartaglia was the winner of the confront. Because the problems Tartaglia proposed to De Fiore was not able to solve it. And the problems Fiore sent to Tartaglia, he solved it because he discovered the formula from Scipione del Ferro. He have discovered that. By some reasons that I don't have time to speak it now, it's some political reasons, money problem also, people convinced Tartaglia to share his formula with Gerolamo Cardano. Cardano is the same, those who like mechanics, is the cardan, that tool you have in a mechanical apparatus, the cardan is the same guy. And he was a very famous one. He is well known in the Milano political circle. So he has sent the formula to Cardano, who published in this book, Ars Magna, which is probably the first big book of algebra in the history of mathematics. And what happens is that Cardano, with this formula, was able to generalize the solution for all cubic equations. He was able to do that, okay? But I have a problem there. As Cardano wrote, it was a kind of mental torture for him, because with that formula, he was able to find the solution for any cubic equation. But as long as he treated the square root of a negative number like any other quantity. This is, for him, was a mental torture. Okay? So, but as we usually say, when life gives you a lemon, you make a lemonade. Okay? And that's what Rafael Bombelli did. He just said, well, if I can beat this, I will use it. And then he introduced in this year, in 1572, the idea of complex numbers. So they appear with Rafael Bombelli in 1572. Well, after this, now the story, I think everybody knows, at least this part, you studied this. Then came the idea, the interpretation of complex numbers in the terms of the Argand-Gauss plane, although it was discovered before Argand and Gauss by this guy, Caspar Wessel, a cartographer, a Norwegian cartographer, discovered it first, but okay. And, well, after that, there is, you know the history, probably some of you know the history of Hamilton. Hamilton, the one of the Hamiltonian. Okay? Hamilton, well, at that time, he was very famous. He had a lot of work. He already did the Hamiltonian mechanics. And for a lot of time, he tried to generalize the idea of complex numbers, the interpretation of them in terms of the geometry of the plane. Okay? He tried to generalize it to the space. So for several years, he said, well, plane, one imaginary numbers, I go to space, two imaginary numbers, or two imaginary units. Okay? For the plane, one imaginary unit, space, two. And he tried a lot, but had a problem. The algebraic system does not close it. It's not closed. The attempts he made were not successful. But one day, in 1843, he did it. In 1843, he tried not to use two imaginary units, but three ones. And then he discovered the quaternions, whose symbols are the age in homage, clear homage to Hamilton. Well, I think some of you know it. The quaternions, you have three imaginary units, I, J, K, all of them square into minus one, but there is a catch. And the catch is that they do not commute. Ij is not equal to Ji. They are minus each other. And the same for the other units. Okay? Those who have studied this see that with quaternions you can describe rotations in your space, three-dimensional rotations. Okay, this is a very interesting algebraic system. But this was a great time. Almost at the same time, Hamilton was Irish. Almost at the same time in Germany, there was a great guy, Hermann Justo Grassman. Okay? And he formulated a theory. The book is the Die Ausdehnung. Can you imagine my Caipira accent speaking German? so he made an algebraic system known as Algebra of Extensions. And this is really, really great. Okay? The idea was very simple. You think about vectors in your first course on vectors and geometry. You learn that, okay, vectors describe a class of equivalence of line segments with same length, same direction, and same orientation. It's an equivalence class of this kind of objects. Okay? Then you say, okay, you have a vector. Then you want to study area, okay, you work with the cross product. Okay? But Grassman, in fact, much before the introduction of cross products, came with another idea. In your space, you have line segments, okay, but you also have plane and plane fragments, and you have volumes. Why you only have line segments? In space, there are other things, other geometric objects. And he said, well, I will try to formulate a product which resembles, in some sense, this product. If you have line segments, the product of two line segments make a plane, a plane fragment. That's his idea. So he introduced a product called, nowadays, the exterior product, such that they anti-commute, like the anti-commutative product of Hamilton. But this has an interpretation, okay? A nice interpretation. Because, okay, you can define an equivalence class of plane fragments. Okay? You have plane fragments with the same area, like the length of a line segment. You have the area. You have the orientation of them. Okay? Sorry, you have the direction. Okay? And you need to have a orientation. And what is the orientation? It's the way you walk through the borders of the figure in a clockwise or an anti-clockwise sense. So you have the orientation, the order you make the product, it shows this, what happens with the orientation. See, here. AB means this product, A and B, so it's oriented in this way. BA, it's BA, oriented in this way. So they have opposite orientations, that's why you have the minus sign. Very simple idea, okay? So, in the same way you have a vector as an equivalence class of line segments, you have here a vector which is the equivalence class of these plane fragments. But, well, I will not use the same name for otherwise you will make confusion between different vectors. So those vectors are related to line segments are called one vector, and this one related to a plane are called two vectors. All of them are vectors, but to distinguish between different vector spaces, we say that this is a two vector. The interesting point is that you can continue with this kind of construction. It's not limited to two. You can construct a three vector. In the same way, related to volumes. Okay? And you can, the orientation of them are made according to right-hand rule or left-hand rule. So you have now a three vector. If your space has any dimension, you continue playing. You have a four vector, a five vector, and so on. This is a big difference between when you have the cross product. Cross product only works in dimension 3. Only 3. Because associated a vector, a normal vector, to the plane. But this is only possible in dimension 3, not in 2, not in 4. Only in dimension 3. And in fact, you can also do this in dimension 7, because of one structure called octonions, but let's forget this. Okay? So you have this kind of structure which works in any dimension. Those of you who have already worked with the differential forms for example, those who work know that. The vector calculus from your second course in calculus, we have a vector calculus, with those terms like Stokes, Green, Gauss, it only works in dimension 3. But if you like to go to higher dimensions, you have to use the differential forms. Differential forms, the algebra of differential forms is the Grassman algebra. Okay? So it does not have this kind of limitation. So in one side, I have the generalization of complex numbers with Hamilton. On the other side, I have the Grassman algebra. Okay? And then some years, well, Grassman, it's a kind of parenthesis. This book of Grassman, Die Aus der Nungelehre, no, before saying that, well, the Grassman algebra, you see, when you close an algebra, you need to work with all kinds of elements. So you have the scalars, as you have the vectors, the one vectors, the bivectors, and three vectors. So the stereo algebra, you have to work with this big space, with this 8-dimensional space. Okay? And the starting point is this one. The Grassman, this is a quotation from Michael Crowell, a very good book, A History of Vector Analysis. If you have the opportunity, read it. It's very, very interesting. And there is this quotation that Grassman book is a great classic in the history of mathematics, even though one of the most unreadable classics. And in fact, when Grassman in 1844, he wrote that book, Die Aus der Nungelehre, nobody read it. Okay? And he was so sad with that he wrote in 1860-something, I'm not sure now, he wrote another Die Aus der Nungelehre, but not a kind of second edition. It's a completely new book. He said, no, now people will read it. Nobody read it. Yeah. With the great exception of one guy, this, William Kingdon Clifford in 1878. What he did essentially the connection between the algebra of Hamilton and the work of Grassman. Okay? And, well, I can introduce Clifford algebra in many different ways, but I try to do it as simple as possible. Okay? This is the idea of the Clifford algebra. Clifford wants to introduce a product of vectors such that the product of the vectors gives the square length of the vector. And how do you calculate the square length of the vector? The square of the components. Okay? Everybody knows how to do it. So I will introduce a product which I'm denoting for this cross box, this boxed cross. Okay? It's a product, I don't know. Let's see what I can do with it. So let's try. Now here I have the expression for the vectors, see, here and here. I want it to be the length, square length here. So I will suppose that my product satisfies the distributivity property. Okay, so I have this expression, and if they satisfy this, and if this has to be true for all V1 and all V2, there is no other possibility than having E1, oops. Then this product of E1 and E1 giving 1, E2 giving 1, and this equals 0. There is no other possibility. Well, there is one choice for solution for this problem. You know one solution for this. It's the usual scalar product. The usual scalar product solves this. Okay? E1 dot E1 is 1, E2 dot E1 is 2, and E1, E2 equal to 0. Well, it solves that problem. Because you see, if E1, E2 is equal to 0, as E2, E1 is also equal to 0, so the sum of both is 0. Problem solved. But this was not solution Clifford did. Well, in order to understand the solution, I will change the notation. This box times is terrible. So now the Clifford choice, I will note by just a position. Okay? So what is his choice? E1, E1, oops. E1, E1 equal to 1, and then this is that equation. And he took this as a definition of the product. So if this is true, E1, E2 must be minus E2, E1. So the problem is, what's the interpretation of this quantity? It cannot be scalar. Okay? It cannot be scalar because a scalar commutes with all vectors. Okay? So you see, if you multiply it on the left by E1, it gives E2. If you multiply it by the right by E1, it gives minus E2. So it cannot be a scalar. So what is this equation? What is the result? What is E1, E2? Well, Clifford knew the work of Grassman. E1, E2 is the bivector. Okay? It's that guy. But, okay, it's a bivector, good and that. But in the algebra, the Grassman algebra, E1, E2, it's the product in Grassman algebra is the wedge. Okay? It's the wedge product. So in the Grassman algebra, E1, E2 product, E1, E2, this is 0. They anticommute here, and then E1, wedge E1, it's 0, because it's always anticommuted. So it's 0. But this is not Grassman algebra. What happens in this algebra for E1, E2 square? So let's calculate it. These are the relations. So E1, E2 square is equal to E1, E2, E1, E2. Then I will use that property to replace that E2, E1. So I'll obtain this. And then E1, E2, each one is squared. The result, minus 1. E1, E2 squared is minus 1. So what do we have? Let's summarize the situation. We have an element, see, in a real algebra. Everything is real here. It's a real algebra. Real vectors over the space, over the field. Okay, the scalars are real. The vectors, everything is real. So I have an element in a real algebra, a positive defined matrix. Every vector squares. Positive is a positive defined metric. And it's representing a geometrical object. E1, E2 is a plane. Represent a plane, a class equivalence of plane, fragments of planes with the same area, same direction, same orientation, and squares to minus 1. So the interpretation for U1 and E2 here is the same interpretation you have in the Argand-Gauss plane. It's the same one. In what sense? It's the generator of rotations. In the Argand-Gauss plane, the imaginary unit generates rotations. As you can easily see, E1, E2 times E1 is equal to minus E2. When it multiplies by E2 equal E1, so what we have, the result of that operation is a clockwise rotation by 90 degrees. And an arbitrary one can be performed in this way, with the exponential of that bivector. So it's exponential of the generator, okay? And you see, then you have an easy interpretation, because if you multiply by I, you have, in here, or E1, E2, the interpretation is the same. You have a rotation by 90 degrees, multiply it 2 times, you have a rotation by 180 degrees. So you have a vector, then you rotate it in the orange, you obtain minus the vector. So the square of it is minus 1. Very easy interpretation. Okay? So this is this algebra that I introduced to you is a very simple algebra. We denote by CL2, 0, 2, because you have two the vectors, you have 2 squaring to plus 1, and no vector squaring to minus 1. Okay? And in this algebra, you have scalars, you have 2 vectors and 1 bivector. This construction is very easy to generalize it to 3 dimensions, okay? And in fact, to any dimension. So in 3 dimensions with orthonormal base E1, E2, E3, you have, in this space, you have 1 scalar, you have 3 vectors, you have 3 planes, independent planes. So you have 3 bivectors and 1 3 vector, you have that thing. And these are the products you have. E1, E2 giving that bivectors, these 3 ones from the Grassman algebra. But you have a D1, the trivector is this. Okay? But what happens with the square of these guys? See, every one, you can easily perform this. You have to calculate this. Every one of these guys, when you square it, gives minus 1. So you have 4 different geometric square roots of -1. But with one difference, E1, E2, E3, it squares to -1, but it commutes with every element of the algebra. Well, you can check this. Trust me, that's true. It's very easy to prove this. So it commutes with everyone, but it's like square root of -1. Square root of -1 is a scalar. It squares to -1, and it commutes with any element you have. It's a scalar. The same with this guy, but this guy is a volume, represents a volume. But you see, the bivector is not the same. With bivectors, they anticommute with one another. These are the relation between them. So these are the relations you have for the bivectors. And you see, these are the relations for the quaternions. So you see that E1, E2, E1, E3, these bivectors, if I associate it with ijk in this way, or possible cyclic permutations of this relation, you see that you have the quaternion algebra here. You have exactly the quaternion algebra with the bivectors. So the result you have, this Clifford algebra, which is the one with 3 vectors, 3 space-like vectors, and no time-like vector here, or in relativity, it's in general, we say that the one squares positive are time-like, okay. But in this Clifford algebra, defined with these elements, you see that it's the complexification of the quaternion algebras. So you have quaternions with the even elements, the scalar, and the 3 bivectors, and with the I here, you have the complexification of it, okay? So what we have? Many different imaginary units in the same algebraic system. Okay? Well, let's summarize what now we know. We have the square root of -1, which is algebraic, the algebraic one. That's solution of x squared plus 1 equal to 0. Everybody know that. But now you see that we have other imaginary units. Okay? We have E1, E2 square is equal to -1, which is a geometric square root because it represents a geometric object. See? And it's the generator of rotations in the plane. I have also now the bivectors also, but in the 3-dimensional case. And then, but these ones also square -1, but they don't commute and represent rotations in space. Everybody knows, simple experience, rotations in space do not commute. And you have D1, E2, E3, square into -1, another geometric, okay? Another geometric square root of -1. And in this algebra, in this very simple algebra. So now let's make the question, formulate the main question. What's the origin of the imaginary unit in quantum mechanics? You have a square root in quantum mechanics of -1 there. Which is this one? What is its origin? So what I will try to, in the rest of this talk, try to answer you is this question. Okay? And, well, everybody knows you have, in quantum mechanics, we start studying Schrödinger equation. And then, well, most of you pass through Pauli equation and go directly to Dirac equation. But that's what you have. You have Schrödinger equation, you generalize it to Pauli equation, and then you generalize it to Dirac equation. And I think it's a big mistake here that you try to interpret quantum mechanics using Schrödinger equation. Schrödinger equation is the most particular case of these equations. It's the less general one. So does it make sense to try to interpret quantum mechanics in terms of Schrödinger equation and then goes to generalize this interpretation to Pauli equation and then generalize it to Dirac equation? Isn't it more meaningful to try to develop an interpretation of what you have in terms of Dirac equation and then goes to Pauli equation and then to Schrödinger equation? It's a good bet, I think. So let's try. What I will try to do is this. Try to have an interpretation, in particular for that square root of -1, starting from Dirac equation. And then from Dirac equation, going to Pauli equation. So then from Pauli to Schrödinger. Okay? So let's remember quickly the idea behind the Dirac equation. What he did, he tried to, everybody knows who have studied that there are problems with with Klein-Gordon equation when you try to interpret it in terms of solutions. You have the problem negative signs and negative solutions. So Dirac tried to formulate his theory, making the factorization of the Klein-Gordon equation. This kind of factorization problem is very easy to be done with Clifford algebras. Okay? This is an expression for the factorization of the Laplacian. And this is, you see, you have E1, E2, E1, E2, E3, they all anticommute with each other. So when you calculate the square of them there, well, each one is square, E1, E2, and E3 squares to 1 in this case. So you have dx, dy, and dz squared over there. The part which anticommute, E1, E2, plus E2, E1 is 0. And because the partial derivatives, when they have the mixed one, they are equal. So it's very easy. It follows very easy this. This is in 3 dimensions. And you can easily go to 4 dimensions. This is the case of Dirac. We have 4 dimensions. And then makes the same with this algebra. You have just to add one more element to your algebra. This new element I have denoted by E0. But with the difference here that you have the relativistic case. So you have vectors which square to plus 1, and you have vectors which squares to -1. Okay? And this is the usual convention you have, at least for field theorists. Usually do this, take this convention. So E0 squares to 1, the other one square to -1. And remember, all of them, okay, they anticommute. All of them have a lot of these products. And in this algebra, you have scalars, vectors, bivectors, and so on. Very easy to do this. The problem Dirac made was this one. He tried to solve this problem. There is a small difference here between this problem and this one. Here, these guys are vectors. See, vectors like any other vector used in your calculations since your first year at the university. These are the same vectors. Here, gamma 0, gamma 1, 2, and 3 are matrices. That's why I wrote this one bolded one here. This is a unit matrix. So Dirac tried to solve this problem, this kind of problem. Notation a little bit different, but essentially it was this problem. And he solved this. In other words, Dirac had discovered Clifford algebras, that one, but using matrices. Matrices, matrix algebras, they are representations of associative algebra. In associative algebra you have, it can be represented in terms of matrix algebras. Clifford algebras, almost all of them are simple algebras, so they can all be represented in terms of matrix algebras. So that algebra I was talking about, which is the complexification of quaternions, is isomorphic to the algebra of 2 by 2 complex matrices. So this is the representation you have from it. So you have Dirac solution, but there is a catch here. So Dirac solved the problem using 4 by 4 complex matrices. This algebra Dirac discovered was not the algebra I told you in the previous slide, which was CL13. I denoted by CL13. It's not the same. It is the complexification of this algebra. The algebra CL13 is the algebra of 2 by 2 quaternionic matrices. Okay? You have 2 by 2 matrices, but the entry in each of the entries of the matrix are quaternions. This is what is CL13. So, but Dirac has not discovered it. He has discovered that one. He has used 4 by 4 complex matrices, and this is not the complexification of that algebra. Sorry, it's not that algebra, but it's complexification. And question, why? Why he did it? Well, I was reading some days ago a very interesting book about the life of Dirac. Okay? It was the strangest man. Very important. Those who know the story of Dirac will know what is meant. He was really a very strange guy. He does not talk with anyone. And he was that, really the picture you have of a nerd. Okay, he was a typical one. Okay, and he knew quaternions. Dirac, sure, he knew quaternions when he formulated Dirac theory. Okay, but by some reasons, I believe he has not worked prefers to not work with some quaternions in his work, probably because the work of Paulo, I think, was very important this way. That's the fact. He knew quaternions, but he has not used it. Okay? And what's the reason for that? So one of the reasons, I believe, is this one. Paulo work on the generalization of Schrödinger equation to include spin uses that Clifford algebra, CL30, the algebra of 2 by 2 complex matrices. So that's what we have. That's what's the situation at that time. Okay. So you have Schrödinger equation in 26. Paulo in 27 introduces his equation using complex matrices. Then came Dirac. How to do it? Okay. See, Schrödinger equation, now I'll try to make some mental exercises here, see what is in the mind of Paulo. So you have Schrödinger equation, one complex degree of freedom in the equation. Okay? And then you have a Pauli equation. He wants to introduce his equation with two complex degree of freedom, because you know at that time the Uhlenbeck-Goldsmith hypothesis about the existence of the spin as an internal degree of freedom to explain Zeeman effect, all of that. So he has to work with two complex functions. Okay? So Pauli wave functions need to have values, okay, in a two-dimensional vector space over C. That's it. But what is this space? Okay? Who is this space? There are many different choices. Okay? Pauli made this choice. Works of C2. So he took this vector, describes the vector state in his equation by a column matrix. Column matrix, two entries, alpha and beta, each one describing the plus and minus, spin 1/2, spin minus 1/2 component of the electron. And here I have not written the space and temporal dependence, just to keep notation simple. So that's what Pauli did. Okay? In 72, a famous mathematical physicist, the Freeman Dyson, in a lecture, it's called Gibbs lecture, he said that you can Google this and you find the paper, okay, and read the paper, it's very interesting to read. He said that he enumerated situations where the progress in physics and mathematics have been retarded by the lack of mutual communication between them, and said that there was some missed opportunities. One situation is, for example, in theory of spinors. When I started studying spinors, it was terrible because physicists made something in one direction, physicists in one direction, mathematicians in another direction, so they make the same thing but with different names. That was terrible. So you have this is a problem in the theory of spinors. And another thing that Dyson has enumerated, I said it was a missed opportunity, is the role played in quaternions in the development in physics and mathematics. Okay? So the dimension of quaternions over C, over the space of C, is 2 also. It's also 2-dimensional. Okay? And you see here, this is the expression. It's easy to see. So quaternions are these objects. You see here are the 3 imaginary units. So it can be easily written this way. So this is complex numbers. Isomorphic to complex numbers. It's isomorphic to C2. So, but if you are using quaternions, you can also use complex matrices. It's okay to use matrices. There is a representation of quaternions in terms of matrices. So this element, this psi, if you want to represent it with matrices, it's a matrix of this form. See, here is alpha, beta, the same in I wrote, see here, this alpha beta. It's the same here. This has the same information as that column matrix. This is two-dimensional, because the other column, you have two columns, okay, but the other one repeats the information you have here. It's the same. You can write it in this way. There is one column, another column here, okay? They are the same, okay? So you can work with this. So my question is, what if Pauli had chosen to work with quaternions instead of C2? The dimension is the same. Well, some possible consequences of this I have discussed in this paper here, in the European Journal of Physics, 2016. I have discussed that. I tried to show in this paper how things would proceed if you have this choice, and how some things would be different today. Okay, it's an interesting reading. Okay, and well, what happens then? Dirac choice was, I think, motivated to use this column matrix here because Pauli has chosen to work with C2. So that's very easy. Okay, if I have used C2, well, now I'm going to C4. That is. But what if he has chosen, sorry, but what if Pauli has chosen quaternions? What would happen here? Okay. So you see, Pauli case, you would have this one, Pauli, this matrix here, sorry, this is, well, when complexified, huh? You can work, not the same. This is inside, sorry, this is inside this because you see, the full algebra is complexification of quaternions. It's a full algebra, but it's inside because see, the two columns are equal, they have the same information, not equal, they have the same information as you see there. So it's a sub-algebra of this one. So my guess, one possible guess would be that Dirac would try to do the same way Pauli did this, he would make the same here, but then with quaternions instead of complex numbers. It's a very natural generalization. If you have this. If you have this choice, okay, the generalization would be this. But you have this choice, the generalization would be this. Here, complex one. A possible generalization would be this. And this is the Clifford algebra. I told you, the representation of that Clifford algebra 1-3. As I said here. This algebra is this one. So, is it possible to formulate Dirac theory with that algebra CL13, which is, on the matrix point of view, this algebra? Well, it is. Yes, it is. But there is a big difference. I'll show you how it is done. But see what is the difference. In the Dirac algebra, the original solution of his problem, it is this algebra. Here you have a complexification of a real algebra. So here you have the algebraic complex I, the square root of x2 plus 1, that solution of that problem, the algebraic one, not the geometrical one. Okay? CL13 is not. There is no algebraic I there, only geometric I. Well, I said I will not talk about the general discussion of this of Dirac theory in this CL13 algebra, sometimes called the space-time algebra. Okay? It's I don't have, of course, time for that. These are some references for that. This is a good book, not a rigorous one, but a very good book by Chris Doran and Anthony Lazenby. Okay? I recommend this. This is for physicists, not very technical, not from the mathematical point of view, but there are a lot of examples, not only in quantum mechanics, but electromagnetism also, and relativity. It's a very interesting book. If you want something more mathematical, you have this book from Pertillo Desto, Clifford Algebra and Spinors. It's a good introduction. He talked a little bit about the use of this space-time algebra in Dirac theory. I have also written a book with Rodão da Rocha, which is a professor, who is a professor at the Federal University of ABC. We have also this book here. And there are many papers from David Hastings in his website. So if you are interested in it, you can go to this website, download it, and read it. Okay? But now let's see how can I represent this Dirac theory in this space-time algebra. The spinor is represented, I need an object with 8 dimensions, okay? If you have here C4, you have 8 real dimensions here. So I need an object with 8 real dimensions. In that space-time algebra, okay, so you have the dimensions 2 to 4, 16, you have to take this element, which is, this psi is composed by elements which we call even degrees, okay? You have no, only multiplications by even number of vectors you have there. So this is the element. This is a very interesting thing that when I write psi in this way, I can show you, so I'll not do it, but one can show that this same element can be written in this expression of this form, where here you have a scale factor. Here, this angle beta where times the volume element. If someone has studied the formalism of differential forms, have studied the Hodge duality operation, these volume elements is the same. The duality operation in this algebra is just the multiplication by this element. It's very easy, just multiply it by it. So you get the duality operation. And it's the same that when you have electromagnetic, the Maxwell equations in vacuum, there is a transformation called duality that transforms electric field in magnetic one and vice versa, which is also of this form. So say this is a duality rotation. And this other guy are here, you can show it that it can be decomposed as a Lorentz boost and a special rotation. Okay? You can show this, it's not easy, it's not easy, it's not difficult. And you can show this. And what you see that this is a kind of generalization of the polar decomposition of complex numbers. In fact, it's just like this. Complex number, the polar decomposition, you have a scale and then exponential of something that generates rotations. That's it. It's the same here. That's very interesting. Okay? But, well, this is not a part of the talk. Okay? So I want now to present to you how is Dirac equation in that space-time algebra. Okay? So I have that psi is an even element of the algebra. But in order to write an equation, I need two things. First of all, I need to choose a time-like vector. I need to make a choice. Okay? So I'll choose a time-like vector, one which squares to plus 1. And for convenience, I will choose it as E0. Okay? This is just a convenience. Okay? I don't need to do it. It's just an n. I just need to choose an n. But for convenience, I will choose it as the same, the basis vector I have. Vectors from my base, I will choose as the same. Okay? And this is important because we need to have these objects. Because in Dirac theory, those who have studied knows that you have some kind of bilinear covariance of the theory. Okay? And then one of them is this, the probability density current, for current. And it's written in this formalism by this expression. This is that psi. Tilde here is an operation that reverses the order of the multiplication. But it doesn't matter, okay? It's just an algebraic operation. So the fact important here is that I need to choose one vector. I'll choose this one. And I also need to choose a space-like vector. Okay? And I'll choose it as E3. I choose E3, I like E3. Okay? I'll choose for convenience this one. And it's important because I need to write another bilinear covariant, which is the spin density. Okay? The spin density associated with the Dirac field. And it is given by an expression of this form. This 1/2 here is because it spins 1/2. Okay? So if you have E0 and E3, you have a bivector, because as I said, the E0, E1, E2, E3 this product, is the volume element of the space, and is the guy that makes the duality rotations. Okay, the same duality you have, as I said, in the Hodge duality operator, the star duality operator. It's the same. It's this guy make this kind of duality. So if you have E0 and E3, when you multiply by this guy, you obtain E1, E2. So you have those two, you have a bivector E1, E2. So as I said, this is equivalent to choose E1, E2. Okay. So now I will show you what is the Dirac equation in this formalism. Is that equation? See why I need to choose a time-like vector and a space-like vector. I have space-like, but here I use the dual of it. So I need these two guys in the equation. They appear explicitly in the equation. Okay, and they have to do that to be there. Well, I can start with Dirac equation in that complexified algebra 4x4 matrix and prove this. I can do this. But I will need at least half an hour. And I will not do this. I don't have time for that. What I have time to do, and this is very easy to see, is that starting for this equation, I will obtain Dirac equation. So I have both ways. I can start from Dirac and prove this. And I can also start from this and prove Dirac. But starting from this and prove Dirac equation is very easy. So because of time, I'll do this, which is, as I said, is easy to do. So here is the Dirac operator written this way. Note that this is different. Here I have vectors, it's not matrices. Okay? This is written only with abstract vectors of the space. So how can I show that equation? How can I show that this equation is equivalent to Dirac? Very easily, just take the matrix representation of each element. Okay? So the E0, the vector, I will use it as matrix representation of it, the gamma 0 matrix, which is written here in standard Dirac representation. Okay? The same for U1, E2, and 3, all of them represented by standard Dirac matrices. They're called standard representations. Okay? And in this way, that psi there, written in this matrix, is this expression for him. See, the column here, all other columns are repeating the same information. So the objects of this space is a 4-dimensional space. Informations are repeating here. No new information here. Okay? And it's the alpha, beta, alpha prime, beta prime are related to these guys by these expressions. So now comes the point. Here is the usual Dirac spinor column matrix. Here, these guys, all the elements of this space are clearly isomorphic to all matrices of this form. Here I put these equal. They are not equal, but they are isomorphic. Elements of this space are all elements of this form. The space of elements of this form is isomorphic to the space of elements of this form, of course. Okay? But see that these guys, okay, they are the same. They can be written in this form, where here I have a matrix with these entries, and here these dots means that it can be any element you want, because when they multiplied by this matrix here with this lot of zeros, they're killed by these zeros, these elements here, in order to obtain this expression. Okay? In particular, I can choose these elements as these guys here, which is the representation of that psi. These matrices of this form are called idempotent. If you remember your course on linear algebra, idempotent matrices. So, and these guys, I told you, they are a representation of an element which I called F, which is of this form. The E0 and E1, E2. Those which I came when I choose the space vectors, the time-like vector and the space-like one. Of course, suppose I don't like to use E0 and E3. I have N and sigma. So my expression, the equivalent expression, would be 1 plus N, and here 1 plus duality of sigma times N. I have a product of both, then take duality operation, which is multiplication by this guy. Okay? It's an expression of this form. So this is the F. But now I have E0, oops, this E0 times F, is easy to see this, is equal to F. And E1, E2 times F is equal to I. This I came here, and this I because it's a matrix representation. Where came this I here? This I, oops, came from here. It's this I. This is the orange of it. See, E2. E2 appears there. You have E2 in that expression. Here you have I from the matrix representation. And when you have these guys, it appears the I here. But the magic is the multiplication by E2, E1. Then it appears here. So now start from the equation in space-time algebra. Take its matrix representation. Everything very easily. Multiply by this F. So you obtain what? You obtain this expression because E0F is equal to F. But E2, E1, F here is equal to I plus F. And this is what it is. This is just the Dirac equation. Because from the very beginning, because of this, I have obtained this one, but because of this isomorphism, it's this. So it's exactly the same. But here you have the I. The I that has appeared in the Dirac equation. And it is this I, when you make decompose this psi in large and small components, and consider the non-relativistic approximation of it, you obtain Pauli equation. This I goes, continue there. And it's this I that goes to Schrödinger equation, when you consider Pauli equation and the limit to Schrödinger 1. So my conclusions, I that appears in the Dirac equation is the counterpart in the matrix representation of the bivector E2, E1. It comes from there. Okay? And why I? Because of the representation of E2. Pauli equation, see, is the non-relativistic limit of the Dirac equation, and Schrödinger equation is a particular case for Pauli equation. So this, as I said, I is, which appears, is the same I. I from Dirac goes to I in Pauli equation, then goes to I in Schrödinger equation. And where came this I? It came from E2, E1. And this guy, E2, E1, came here because of choice of this sigma that I chose as sigma 3. Sorry, E3, which associate E3 or E1, E2 is the same with spin. This guy is E3. I need to choose it because it measures the direction of the spin. And this is the expression for spin density. Okay? Just to finish, I think, how many time I have? How much time? 5 minutes, okay. Just to show, I think it's more easy to see this when you go from this CL13 space-time algebra to its space algebra, this algebra from the Euclidean space. In fact, you can formulate Dirac theory only in that algebra of space that I was describing in the very beginning. Okay? And in this, I cannot show this, I don't have time for that, but it does not matter. So this is the equation in this algebra. That one, CL30, isomorphic to the algebra of 2 by 2 complex matrices. Okay? So in this algebra, the expression for Dirac equation is this one, where well, psi here I have the Laplacian. Here, time is not a vector anymore because I have only 3 generators, 3 space generators. Time is a scalar. Time is a scalar, but the theory is completely relativistic invariant. Okay? Here I have psi E1, here each one squares to -1. I here is -1, but see, the moment operator, it's I and E3, see, this I here is different. This I is E1, E2, E3. E1, E2, E3, and times E3, this is equal to 1, so it's E1, E2 ahead. So you see that in the momentum operator, you have the E3, which is, well, the spin direction. So this beta I have here, this beta here, is very interesting that the definition of it is defined in this way. In a product, an arbitrary product, two elements, and when acting on vectors, it gives minus E3. And well, from this, so it's clear that beta squared is equal to 1. And if I denote the vector by its alpha, just a notation, you can show easily these expressions. If you go to the original Dirac paper, he works with matrices alpha and beta, and these are the relations that he'll be taking in the paper. These are the original ones. Go there, see the original paper, you see this one. But here, you see, and it's the algebra CL30. In Dirac, so here, alpha are matrices, but a beta is not a matrix. It's an operation on a matrix. Probably some of you have already read that the solution to this problem cannot be done with 2x2 matrices. So that's why Dirac used 4x4 matrices. Okay, this is true. This is true as long as alphas and betas are matrices. But there is a solution to this problem if you think of, okay, alpha are matrices, but beta is a matrix operation, a multiplication. Okay? If you multiplication of a matrix, this is an operation. You can define this as a matrix as an operation. The operation is multiplication by A. Okay? An operation on a matrix, given by this. Very simple. But it's possible to have also other matrix operations, like taking the emission conjugation. This is another operation on a matrix. Okay? This beta here, when you interpret this as a matrix operation, it's taking the classical adjoint of a matrix. When you want to invert a matrix, you take its classical adjoint and divide it by the determinant of the matrix. This is how you do the inversion of a matrix. Take the classical adjoint and divide it by the determinant. So this beta is operation that perform and take the classical adjoint of the matrix. So you have a solution in terms of 2x2 matrix, as long as beta is itself not a matrix, but a matrix operation. This is so as in the original Dirac formulation that you obtain. So for those who are interested, want to read more about this, I have written some papers. As I told you, one is this in the European Journal of Physics, where I started thinking, well, what if I have chosen to work with quaternions instead of C2? And then I show that this beta is really the adjoint. Take the adjoint, the classical adjoint. Show this explicitly, say, oh, this property has to be satisfied, and then there's another one, and the guy is this. Okay? So, and if you introduce some more basic introductions to Clifford algebras, are in these two papers. I wrote this in the Brazilian Journal of Teaching of Physics. Okay? And there is also papers from David Heston's website, and a group from Cambridge. There are many interesting papers there also. It's a good reading, so those who want to learn more about this. And, well, I talk a lot. That's all. Thank you very much. Thank you.
So, time for questions.
So I have a question in the very beginning of your seminar where you showed the algebra between the e's. So you wrote some sort of expression like e squared is equal to -1. That was your result. So that isn't Grassman algebra, is it? It's Clifford algebra.
Clifford
right?
algebra, yes.
So how can you generate Grassman algebra from that choice you made from that product and those vectors?
Pardon. Okay, it's not Grassman algebra. Please continue.
Yeah. So how can you generate Grassman algebra from those expressions you have right in the beginning of your seminar?
Okay. Well, there is an easy answer and there is a difficult, solid answer. Okay. The easy answer is you have take arbitrary case. The wedge product of two vectors is the antisymmetric. VU minus UV. This is the antisymmetric part of the Clifford algebra. Is the wedge product and the dot product is the symmetric part. So you can decompose the product of a vector, arbitrary product. So U1 and U2, they are orthogonal. So you don't have this part. So U1 and U2 is just the Grassman product. Is this what you asked this?
Yeah, I think because in the Grassman algebra you have the square of any Grassman number should be 0, right?
Okay.
So that's
So here, if you take this one and then make this you have to consider, in general case, the totally, completely antisymmetric part of the elements of the Clifford algebra. Here it's easy to write it's the totally the antisymmetric part of the product of two vectors. But if you have, in this case, this guy product with another one, you have 16 elements, so you have to consider even all the permutations of them. Write a big expression, but you obtain that it's 0. Okay.
Okay. And can I make another question?
But so just I thought this is the easiest answer.
Okay.
The
complicated one.
The complicated one, but which I prefer, is this one. I like to look. I oversimplified some things here, but I like to look to Clifford algebras as the algebra of operations over Grassman algebra, the endomorphisms of Grassman algebra. You have the linear transformations of a vector space to a vector space. Knowing linear algebra, start studying this. But what if you study the linear transformations of the Grassman algebra? You have the Grassman algebra and study all the linear transformations you have from it. So you can show that the algebra of all these transformations is the sum of the algebra. Suppose the space has any dimension. So you have all the transformations of Grassman algebra, okay, of dimension n, endomorphisms of the algebra, transformations of the algebra inside the algebra. You can show that it's a direct sum of two Clifford algebras of opposite directions. It's like the algebra of creation and annihilation operators in quantum mechanics, but here in finite dimensions. So I like to introduce this in this way, because in my opinion, Grassman algebra is more general than Clifford algebra.
Okay.
And why is more general? Because you don't need to construct the wedge product. You don't need to use metrics. Okay, you don't need metrics.
And in Clifford you need. In Clifford you need.
In Clifford you need. Okay, so it's more general, Grassman algebra. So the way I prefer to attack the problem is first construct algebra Grassman algebra, and then make Clifford algebra from this as kind of creation and annihilation operators of the algebra. Okay, but I cannot do this. I tried to oversimplify things.
Yeah, sure.
Okay, but this is the hard and mathematically sounded one, and show the deep meaning of the two. Grassman algebra is more general because you don't need metrics. That's it. So,
and, my other question was about this thing of matrix operation you thought about. I didn't catch it very well because when we solve Dirac's equation, we find a matrix, like for beta. We find a matrix like 1, 1, and minus 1, minus 1. So what's the difference between a matrix operation and a matrix?
No.
In the beta you showed, like...
No, I'm saying here you can interpret the product as a matrix operation on a matrix.
Yeah.
Okay. And the other one, M1, M2. Another one, it's take the Hermitian conjugation. For example, okay, what I said there is that, well, we can interpret that beta there not as a matrix, but as an operation on a matrix. Then you have a solution to that problem of factorization that Dirac wants using 2 by 2 complex matrices.
But
Okay?
it is not formally wrong to say that it's a matrix, is it?
No, if you want a matrix, then you need 4 by 4 because you don't have 4 linear independent objects.
Oh, okay.
If you want it to be a matrix, okay, you want it. But then you cannot work, you don't have solution to the problem using 2 by 2 complex matrices. Then you need to go to 4 by 4. So if you want to 4 by 4, as Dirac did, so it's nature for you to think, oh, these objects act on elements of C4. That's natural to choose this. But if you choose another way, so you have another solution to the problem.
Okay.
Okay?
Thank you.
Okay.
Can you ask later to him? Okay, sorry. So coffee break, 20 minutes. Okay. And come back to the presentations of the students. Thank you so much
Thank you.
for Professor Jayme.